The next target that we're going to look at is protein synthesis. Now, our cells, of course, undergo protein synthesis. We have ribosomes which translate RNA into new proteins, as do bacteria, but the actual components of the ribosome are slightly different, and so the antibacterials which target protein synthesis are all targeting those slightly different ribosomes that occur in bacteria. Again, like the beta-lactams, like the penicillins and the cephalosporins, these drugs were derivative of the naturally occurring substances produced by another set of moles, the Streptomyces moles. And as I said, they all act to bind to points on the bacterial ribosomes and mess up or inhibit protein synthesis. So the drugs that act this way include tetracyclines, very widely used antimicrobial drugs, the aminoglycosides, the macrolides, the lincosamides, the oxazolidinones, and chloramphenicol. So those are the major groups of drugs which operate in this way. Most of them are bacteriostatic. Some are bactericidal at high doses. If you use enough of them, they will actually kill bacteria. So there they are again. These are the major groups of drugs which work by targeting protein synthesis in the bacteria. The tetracyclines, you can recognize them because of their cyclin endings. So you've got doxycycline, tetracycline, minocycline, cycline. Whenever you see cyclin, you've got a tetracycline there. The macrolides, erythromycin, azithromycin, clarithromycin. Now there are a lot of mycins around, mycin and mycos indicating fungus, so it's really sort of talking about their origins, how these drugs were discovered. So don't let the mycin throw you off, because there are a lot of drugs belonging to other groups which end in mycin. But thromycin, says macrolides, so erythromycin, azithromycin, clarithromycin. Lincosamides, there is really only one drug in that group currently which is used, and that is clindamycin. Then we have chloramphenicol, which is a drug on its own, it's an agent on its own, and then another group of drugs, the aminoglycosides, which include neomycin, gentamicin, and tobramycin. Now we'll see as we go through these, don't become overwhelmed by how many we're talking about, because you'll see that there are some general principles which are applying. I'm sure you recognize the tetracyclines. You've probably all taken a tetracycline at one time or other. But these drugs that we have come to use and to know so well as antibacterials are now all suffering from serious resistance problems. In other words, we have bacteria that are resistant to a lot of these very widely used drugs, which is why other drugs are having to come up. Other drugs that we wouldn't otherwise be using because either they're toxic or they don't have a particularly good spectrum of activity are now coming into play. So there are some drugs here that you will see that are or not widely used anymore, or not widely used at the moment. But the reason that we're having a bit of a rundown of all of these is because the situation is changing. The drugs that have been widely used because they were so effective are now less effective, and therefore there's no point in using them in a lot of situations, and so the drugs that weren't widely used because they were usually more toxic, produced more adverse effects, are now having to be brought into use because they are the only ones that the bacteria are still sensitive to. So let's have a look through these groups, or at least some of these groups. So the tetracyclines. These are produced by molds present in the soil. They were the first really broad spectrum antibiotics to come about. The penicillins at first at least were rather narrower spectrum. These were always broad spectrum, effective against both gram-positive and gram-negative bacteria. They have been used for many infections because of their broad spectrum, so that if you went to the doctor and it appeared clinically that you had some kind of bacterial infection, and sometimes, let's face it, people weren't even too picky about determining that it was a bacterial infection as opposed to a viral infection, you would be given a broad spectrum antibiotic. Basically, there would be no need to actually take a sample, to culture that sample and find out exactly what bacterium it was. You were given a broad spectrum antibiotic. The idea was that it would kill everything anyway, and so there wasn't any point in having a look to find out what it was. Now, resistance is making tetracyclines less useful, so bacterial resistance is now meaning the use is dropping down. What else can we say about them? Tetracyclines have this capacity, or they have a tendency rather, to bind to divalent and trivalent cations, metal ions in particular. So they'll bind strongly to calcium, a divalent cation, to magnesium, to ions. The tetracyclines have the tendency to bind to those ions. Now, because they bind strongly to calcium, they will tend to concentrate in places in your body where calcium ions are also absorbed and part of the structures. So they will be concentrated in the enamel of teeth, for example, in the structure of bones, and in tumours which are calcified. So wherever calcium is laid down, if there's tetracycline around, then tetracycline will be laid down complexed to that calcium as well. This makes them teratogenic, so you would not give them to somebody later on in their pregnancy, because as the teeth and bones are laid down, they will be included in it. And so they can cause this discoloration of teeth, which is known as tetracycline teeth, which you do see in people still. Before it was discovered and known that tetracycline had this tendency, this brown, almost stripy discoloration of the enamel of the teeth as a result of the presence of tetracycline in there. Also, you can get these effects in kiddies who are growing, and the bone is being laid down and the rapid growth, and also teeth, so they're contraindicated in kiddies also under 8 years of age for that same reason. Because they form these complexes with those cations, if you take, for example, antacids, which have a lot of metal ions in them, calcium, magnesium, aluminium and so on, there's no point taking tetracycline along with those, or within a couple of hours of taking an antacid, because most of your tetracycline won't get absorbed because it will be bound up, complexed by those calcium or aluminium ions in your antacid preparation. So that's one of the pieces of advice you'd always get if you were given a tetracycline, is don't take it with milk, obviously, which contains calcium, or any other preparation that would be high in those kinds of ions. One more thing that I will say about tetracyclines is that some of them, and doxycycline in particular, but a number of them to a certain extent, have potential for causing esophagitis. That is, when you're swallowing them, they can cause irritation and swelling of the esophagus, which can be quite painful, or can give you that feeling of something stuck in your throat. So again, particularly if you were taking doxycycline, you would be told to take it with a big glass of water, so you wash it down very quickly, and to remain sitting upright after you've taken it, so that you get it washed down through the esophagus as quickly as possible and minimize the chance of it causing that esophageal irritation. So that the advice would be, if you've got a doxycycline tablet to take, never take it with milk, and don't take it lying down, which is quite good advice generally, really. So those are the tetracyclines. Now this is for interest rather than for assessment purposes, and I'll put it there really for you to just have a look. This is really just to bring home to you how widely used the tetracyclines have been, how useful they have been because of their broad spectrum. They have been able to nobble a whole range of infectious illnesses, and now we're having to look for other drugs to take over some of these drugs, but they are still effective against a number of things. For example, if you were going to a malaria area, you could well take doxycycline prophylactically to destroy the protozoan that causes malaria, and that's not a bacteria, but it's also effective against other things that aren't bacteria. So very useful drugs, the tetracyclines. So another group of drugs, again we're staying on the drugs that nobble bacteria by inhibiting protein synthesis, and these are the macrolides, the thromycins, clarithromycin, azithromycin, erythromycin. Their broad spectrum, very good against both gram-positive and gram-negative. They're often used to replace the beta-lactams if people are allergic. So you can go to the macrolides if somebody's allergic to penicillins or cephalosporins, or you're worried that they might be. They're also used in the triple therapy for Helicobacter pylori, the gastric bacteria that is associated with peptic ulcers. Remember, the standard therapy for that was 3 drugs, 2 of them antibacterial drugs, and the remaining 1 a proton pump inhibitor that reduced the acidity of the stomach. Well, one of those antibacterials is usually clarithromycin, and the other one is amoxicillin. So the triple therapy would be a penicillin, a macrolide, and your proton pump inhibitor. Another thing that is worth mentioning about the macrolides is that they inhibit the CYP3A4 enzyme. So P450 enzymes, remember we talked about metabolism of drugs. A drug that inhibits those enzymes is going to lead to an elevated level of a whole load of other drugs. So they have a potential for causing lots and lots of drug interactions. So if you're taking the macrolides and you're taking any other drugs, you've got to be very careful to check that you're not going to start to get side effects from your other drug as a result of the inhibition of its metabolism. Lincosamides, the one that you may see used is this one, clindamycin. Again, they're antibacterial by virtue of their ability to inhibit bacterial protein synthesis by inhibiting portions of the ribosomes. One of the problems that limits their use is that they have quite a high risk of producing that pseudomembranous colitis due to overgrowth of the bacterium Clostridium difficile. Clindamycin is the one which is particularly known for being able to do this. Not all strains of that Clostridium difficile are going to cause serious illness. It seems to be particular strains that have this sort of virulence. Infection with Clostridium difficile can be produced by any antimicrobial because you're knocking out the whole range of flora that you normally have in your gut. But clindamycin is one of the drugs that it's seen more commonly with, which limits its use. And the aminoglycosides are another group of protein synthesis inhibitors. These include gentamicin, tobramycin, neomycin. So we're seeing the mycin again. These are very powerful drugs. They're bactericidal. They're really quite potent at knocking out bacteria. Only one of them is available orally, and that's neomycin. The other ones are for parenteral use only. And these tend to be held in reserve. These are not your first-line drugs. They're kept for serious infections, life-threatening infections, when we've got resistance, other agents have failed to knock out the infection, or when you can't use other agents. So this group of drugs is kept in reserve, essentially. They're not going to be the first ones to be wheeled out, and you can see why. They have much more potential to be toxic. Nephrotoxic, in other words, toxic to the kidney, neurotoxic, toxic to the nervous system, and ototoxic, toxic to the ears, so they can cause damage to the hearing. So those are the aminoglycosides. Keep away from them unless you've got no other choice, essentially, and they're particularly useful for gram-negative bacteria. Chloramphenicol. You can see, I hope, the order that I'm putting these in is from used most coming first to used least coming later. Chloramphenicol is a very broad spectrum drug. It acts again by inhibiting protein synthesis. It's been around for a very long time. The reason that it is still around is because of the developing resistance, because again it has some serious toxicity problems, which means that you wouldn't use it unless you really had to. It can really depress bone marrow function, leading to aplastic anemia, which can be rapidly fatal. So you certainly would hold off on using it systemically unless you didn't have any other choice, really. So you would only use it systemically if there was a severe infection which you were failing to be able to treat with anything else. And by severe infection we mean something like bacterial meningitis, which if you couldn't get on top of the bacteria would cause the death of the person, and similarly with typhoid. But it is available in various topical preparations. For example, it's available in eye drops. So very small amounts, if any, would be absorbed into the bloodstream. But still, if you're putting it in your eye or on any mucosal membranes, you would have to accept the possibility that some of it is going to be absorbed and get into the circulation. So even as a topical preparation, there are other agents which would probably be used before chloramphenicol because of its potential to be toxic to the bone marrow. And it is now available over the counter in topical preparation. It's one to look out for. It does have quite a severe liability, very useful if there's nothing else, but even with topical preparations you would use it with care and treat it with respect.